This is Lesson 4 in our Calculus 3 series, the cross product. Before we define the cross product, we'll start with a definition of the determinant. The determinant of a 2 by 2 matrix or array of real numbers, here's our matrix A1, A2, B1, B2. We put these bars around it to denote that we're going to take the determinant, and the determinant of this 2 by 2 array is A1, B2 minus B1, A2. So we're multiplying A1, B2 minus B1, A2. And that's our 2 by 2 determinant. So for example, if we have the matrix 1, 2, 3, 4, its determinant is going to be 1 times 4 minus 3 times 2. And that's going to give us a negative 2. Now let's take a look at the determinant of a 3 by 3 matrix of real numbers. So we're using the same notation, those bars outside the matrix, but now what we're going to do is we're going to break this down into minor determinants. So we're going to go across the top row, A1, A2, A3. We're going to put our A1 here, and then to find the 2 by 2 matrix that's going to be here, we're going to block out the row and the column of A1. And so we're left with B2, B3, C2, C3, and that's what goes here. Similarly, when we're ready for A2, we notice that there's going to be a negative sign. We're going plus, minus, plus. So positive, negative, positive. There's a negative sign here, and then for A2, same thing, we're going to block out the row and the column of A2. So now we've got B1, B3, C1, C3. And similarly for A3, so we have B1, B2, C1, C2. And then these 2 by 2 determinants are computed as we just saw above. So for example, this matrix here, 1, 0, 3, 2, negative 1, 5, 4, negative 2, 4, we're going to break it down into its minor determinants. We're going across the top row with a positive, negative, positive. So we have positive 1, negative 0, positive 3. And those minor determinants are found by blocking out the row and column of that leading term. Now computing these minor determinants, we have our 1 on the outside, and then we have negative 1 times 4 minus negative 2 times 5. 2 times 4 minus 4 times 5. 2 times negative 2 minus 4 times negative 1. And so this determinant comes out to be 6. Now we're going to use this 3 by 3 determinant to define the cross product of two vectors. So in the last lesson we asked the question, is it possible to define a multiplication of vectors where you would get some useful quantity? And in the last lesson we talked about the dot product, which is a scalar multiplication of vectors. You're multiplying two vectors and you're getting out a scalar. Now we're talking about a multiplication of vectors that is a vector product. So we've got A cross B, and our result is going to be a vector. So we're going to start by setting up our standard basis vectors I, J, K in the top row. Then if we're doing A cross B, the components of A go in the next row, and then the components of B. And then we're going to take our determinant just like we did above. So for example, if A is 2, 0, negative 1 and B is 0, 3, 2, then A cross B is going to look like this in 3 by 3 determinant form. And then we're going to continue to compute that determinant. So multiplied by vector I, we get the minor determinant here, 0, negative 1, 3, 2. And then we have a negative sign. Multiplied by basis vector j, we have 2, negative 1, 0, 2 as our minor determinant. And for basis vector k, we have 2, 0, 0, 3. And so again, computing these 2 by 2 determinants like we saw earlier, we have 0 times 2 minus 3 times negative 1, 2 times 2 minus 0 times negative 1, 2 times 3 minus 0 times 0. And so this gives us 3i minus 4j plus 6k. And we could leave it like that or put it into component notation. But I want to keep in mind here, and I'm gonna write it down so that we don't forget, that this is a vector product. The result is a vector. Right here we have a vector result. So now let's take a look at what these vectors would look like in three-dimensional space. So here is vector A, 2, 0, negative 1, and vector B, 0, 3, 2, and the cross product, 3, negative 4, 6. So we're coming out 3 over negative 4, up 6. Let's take a look at another example. I cross J. Remember now, I is 1, 0, 0. J is 0, 1, 0. So this vector I is going here, right? This is I, and this vector J is going here. These are the standard basis vectors that go in the top row for any cross product. So now setting up our minor determinants looks like this. And it's very nice when we have lots of zeros. Computation is easy. And we end up with 0i minus 0j plus 1k. So I cross j is equal to k. I cross j is equal to k. Now let's take a look at this theorem. Vector A cross B is orthogonal to vector A and orthogonal to vector B. Now it's clear from this nice example that we just had with I, J, and K, but we're going to go through the proof to show it in general. Vector A cross B is orthogonal to A and orthogonal to B. Well, how can we show that vectors are orthogonal? We learned in the last lesson that A and B are orthogonal if and only if their dot product is equal to 0. So what we need to do is show that the dot product A cross B dotted with A is equal to 0, and A cross B dotted with B is equal to 0. So let's first compute the cross product A cross B in general. So for basis vector I, we have A2, B3 minus B2, A3, that's here. For J, we have A1, B3 minus B1, A3, and that has a negative sign out front. For K, we have A1, B2 minus B1, A2. And now we want to take this and dot it with vector A. So that means we need our I component here multiplied by A1 plus our J component here multiplied by A2 plus our K component here multiplied by A3. Multiplying out looks like this, and we notice that all our terms cancel. A2, B3, A1, here's a negative A2, B3, A1. Here's a negative B2, A3, A1. Here's a positive B2, A3, A1. And these as well cancel, and we get 0. So A cross B dotted with A is equal to 0, and therefore A cross B is orthogonal to A. And a similar computation will show the same is true when you dot with vector B, and we'll leave that as an exercise. Now we have another theorem. If theta is the angle between vectors A and B, again with theta between 0 and pi, then the length of A cross B is equal to length of A, length of B, sine theta. So the key here with the proof is to use everything squared. We're going to show that this length squared is equal to length of A squared, length of B squared, sine squared theta. And then we'll take the square root of everything, but keeping in mind that this length must be positive, these lengths must be positive, and also since theta is between 0 and pi, we know that sine theta must also be positive, and therefore we can take the square root of both sides and we'll be good to go. So this is what we're looking to prove. Okay, so we're going to start with A cross B, and its length squared is going to be its first component squared plus its second component squared plus its third component squared. So we're here so far. Now multiplying out is going to give us all of these terms here written in black. a2 square b3 square minus 2a2 b3 b2 a3, right, that's coming from here, plus b2 square a3 squared. And similarly for the other two expansions here. And what is it that we're trying to equate this to? We need for this to look like length of a squared, length of b squared, sine squared theta. And I wouldn't expect you to come up with this idea on your own, but now that you're seeing it, hopefully you'll be able to reproduce it. We're going to add and subtract in the terms a1 squared, b1 squared, a2 squared, b2 squared, a3 squared, b3 squared, because we want to regroup our terms in the following way. We want to take the ones that are bracketed in red here, the a2 squared, b3 squared, b2 squared, a3 squared. We want to take all these that are bracketed in red with these that we added in, and that's going to give us the product a1 squared plus a2 squared plus a3 squared multiplied by b1 squared plus b2 squared plus b3 squared. And the remaining terms, along with these negative ones that we subtracted in as well, are going to give us a1b1 plus a2b2 plus a3b3 quantity squared. Again, I wouldn't expect you to think of this on your own, but now that you're seeing it, hopefully you'll be able to reproduce it. And now we recognize that this is the length of a squared multiplied by the length of b squared minus, this is a dot b quantity squared. Okay, now we're getting somewhere. We need length of a squared, length of b squared, sine square theta. That's what we're looking for. What do we have so far? Length of a squared, length of b squared. Well, we don't have a sine theta here, but we have a dot b. Well, what do we know about a dot b? A dot b is length of a, length of b, cosine theta. So this squared is length of a squared, length of b squared, cosine square theta. Now if we just factor and replace the 1 minus cosine squared with a sine squared, we have the right-hand side that we're looking for. So we have proven that length of a cross b is equal to length of a, length of b times sine theta, where theta is the angle between a and b. Now in the above example, we had vectors a, b, and we found a cross b. We can find angle theta now that we have our new formula. We know the length of a is radical 5, length of b, radical 13, and the length of a cross b, a little more computation to do there, that's radical 61. And so how can we find theta? Radical 61 is equal to radical 5 times radical 13 times sine theta. So theta is approximately 1.32 or 75.6 degrees. And that gives us this angle between A and B. In the other example above, I cross j equals k, we know that the angle is pi over 2. So let's just verify that both sides of this equation are equal for this example. We calculated that I cross j was equal to k. So on the left-hand side here, we have the length of k, which is 1. K is a unit vector. And on the right-hand side, we have length of I, length of j, which is 1 times 1, and sine of pi over 2, also 1. So yes, in fact, this equation does hold for this example. One thing we want to keep in mind here with our cross product being a vector that is orthogonal to the other two is that we have the right-hand rule going on here. So just as we talked about the right-hand rule when we were setting up our x, y, and z axes, the same right-hand rule will help us here to figure out where our vector a cross b will be. So if we curl our fingers of the right hand from vector A to vector B, then our thumb is going to point in the direction of A cross B. Because remember, the vector that comes down in the opposite direction is also an orthogonal vector to A and B. But that's not the one that the cross product gives. The cross product will give the one that your thumb is pointing to. The vector that's pointing downward is negative of A cross B, and that's the vector you get when you compute B cross A. Okay, now let's take a look at this corollary from the previous proof. Two non-zero vectors A and B are parallel if and only if their cross product is equal to the zero vector. Let's recall, vectors are parallel if they are scalar multiples of one another. If we have vectors that are scalar multiples of one another, that means they're either going in the same direction or opposite direction, and that means that the angle between them is either 0 or pi. So if A and B are parallel, then sine of that angle must be equal to 0. And if sine of that angle is equal to 0, then we know the length of the cross product is also equal to 0, and therefore A cross B must be the 0 vector. If the length of a vector is equal to 0, it must be the 0 vector. Just pay close attention to what's written here. Notice that this is the length of a vector, so this is a scalar quantity, and so this is just plain 0. But here we're talking about the vector quantity A cross B, so we're talking about the 0 vector here. Conversely, if A cross B is the 0 vector, then the length of A cross B is equal to 0, and therefore 0 must be length of A, length of B, sine theta. Well, we know length of A and length of B are not 0 because they're non-zero vectors, so that means sine theta must equal 0, and then theta is equal to 0 or pi. And that tells us the vectors must be parallel. Now let's take a look at some properties of the cross product. Unlike the dot product, the cross product is anti-commutative, which means we have a negative sign when we switch the order. So A cross B is equal to negative B cross A. Similar to the dot product, we can multiply a scalar C into either vector A or vector B, or after we take the cross product and it's all the same. We have a distributive property with the cross product, similar to dot product. Property 4 says A dot B cross C is equal to A cross B dot C, so that's an interesting computation to check out. And we're going to show the computation for 5, the proof of 5. A cross B cross C is equal to A dot C, remember that's a scalar, times vector B, minus A dot B times vector C. So we're going to start with A cross B cross C. So let's take a look at what that looks like. A is vector A1, A2, A3, and if we take a look at B cross C, we get in component notation B2C3 minus C2B3, C1B3 minus B1C3, and B1C2 minus C1B2. And now we want to take the cross product of these two vectors. So we put them in the determinant form, and we compute our minor determinants, and so far we're here. So we're looking for a coefficient times vector B minus a coefficient times vector C. So when I look at what we have computed so far, I'm looking for a B1 that I can pull out here with I, and a B2 with J, and a B3 with K, and a C1 with I, and a C2 with J, and a C3 with K, so that we can isolate the B and C vectors that we're looking for here. So when I multiply out the terms, I recognize that I have some terms in the I-coordinate that have B1 in them. So I have A2B1C2 and A3B1C3. And those I want to collect together because I recognize that I'm going to have to factor out the A2C2 and the A3C3 and in order to get the right-hand side that I'm looking for. Again, A dot C times vector B and A dot B times vector C. Similarly with the purple brackets here, these are the terms that we have for our vector C. But when I look at them, I don't have all the terms that I need. When I recollect them, I see I have A2C2 plus A3C3B1I. And what would I need if I had A dot C times vector B? A dot C also should have an A1C1 here as well. What I recognize here is that I need to add in an A1, B1, C1I. And then I also need to subtract it out. I need the same term here. I don't have an A1, B1 to go with my C1I here. So I need an A1, B1, C1I that I'm subtracting out. Similarly, for the second component, we need an A2, B2 C2j. And to subtract out the same term here, A2, B2, C2j. And an A3, B3, C3k. A3, B3, C3k. Then we can regroup and we get our A dot C times vector B from these terms here, and our A dot B times vector C here, which is what we needed. And so that's the computation for property 5. Now let's take a look at this example. Find a vector normal to the plane containing the points 3, 0, 4, 1, 0, 1, and 2, 3, 0. Well, first of all, what does it mean for a vector to be normal to a plane? The idea is the same as orthogonal or perpendicular, just that we use the phrases in different instances. I don't want to say we use them interchangeably because we don't, but they all mean the same thing. So we're looking for a vector that essentially is going to be perpendicular to the plane, but we just use the word normal instead. Well, what do we know so far? We just found out how to find a vector that is orthogonal to two other vectors. So we need a vector that's orthogonal to a plane containing 3 points. Okay, we know how to find a vector that's orthogonal to two vectors. So can we make two vectors out of these 3 points? We certainly can. And that's what we want to do. We want to make vectors, two vectors out of these 3 points, and then find a vector orthogonal to those two vectors. So I'd like you to pause the video, please, and work on that. First thing you want to do is create your two vectors from these 3 points, and then you want to take the cross product of those vectors to get your vector that is normal to the plane containing those points. Please pause the video. I started by labeling my points P, Q, and R, and I looked at vector PQ and vector QR. PQ, I do 1 minus 3, 0 minus 0, 1 minus 4. And so I have negative 2, 0, negative 3. And for vector QR, 2 minus 1, 3 minus 0, 0 minus 1. And what did we say we want to do with these vectors? We want to take their cross product. But I'm looking at vector PQ, and I don't want to deal with these negatives. So instead, why don't I take vector QP? Because then I won't have to worry about carrying around some extra negative signs. And remember, we were asked to find a vector that's going to be normal to the plane. And to do that, we need to just find two vectors in the plane. So it doesn't matter what vectors we're choosing, as long as we find two vectors in the plane. So I take my cross product here, and that gives us negative 9i plus 5j plus 6k. And that is our normal vector to the plane containing points P, Q, and R. Let's take a look at what this looks like in a sketch. Well, here are points P, Q, and R. So here is vector QP, and here is vector QR. And so I tried to sketch there in blue the plane containing those 3 points, or we could say the plane containing the two vectors. And the vector we found that it's normal to the plane, I plotted from one of the points that we had. I plotted it from 1, 0, 1. It doesn't have to be plot there. Remember that a vector is a vector wherever you move it in three-dimensional space, because it's only talking about its magnitude and direction. So it's the direction here that is the normal direction that is perpendicular to this plane, right? So it doesn't matter where I plot it, but I just thought it'd look nice coming out of one of the points that we had. So I plotted it through 1, 0, 1. So from there, I went back 9 in the x and over 5 in the y and up 6 in the z. And so there's our vector. One last thing in this lesson, the area of a parallelogram. So remember that the area of a parallelogram is given by its base times its altitude. So if we have a parallelogram defined by vectors a and b that make up adjoining sides of the parallelogram, then the altitude can be given by length of b times sine theta. So that the area of the parallelogram, base times altitude, is going to be length of A, length of B sine theta, which we just learned was the length of the cross product, A cross B. So to find the area of the parallelogram, we can find the cross product, A cross B, and take its length. So for example, if we have the parallelogram formed by A 2, -1, 5, and B 0, 2, 3, we can take the cross product A cross B, which gives us -13i minus 6j plus 4k, and then take the length of that vector, and that gives us radical 221. That is the area of the parallelogram. And we'll conclude our lesson on the cross product here.